The types of limits we've considered so far in using L'Hopital's rule are what we've called indeterminate quotients. Another type of limit where we can use L'Hopital's rule is called an indeterminate product. An indeterminate product occurs when we have the product of two functions, f and g, and one of them is approaching 0 in the limit and the other is approaching infinity. As a result, we have a product of the form 0 times infinity, and again it isn't clear what the ultimate value of this limit will be. Again, there's a sort of tension between the two functions. If the function f is approaching 0 more quickly than g is growing, then we would expect the limit to be 0. On the other hand, if the function g is growing more quickly than f is approaching 0, we'd expect the limit to be infinite. And of course, if the function f is approaching 0 at about the same value as the function g is growing, we might expect the limit to be some finite number. And again, what we're going to do is use L'Hopital's rule to compute these types of limits. And the way we're going to do this is we're going to convert an indeterminate product into an indeterminate quotient. And we can easily do that in the following way. We can take any product of functions f and g and we can rewrite them as the ratio or the quotient of functions. One possibility is to write f times g as the ratio of f over 1 over g. The other possibility is to write f times g as the ratio of g over 1 over f. In the first case, our indeterminate product turns into an indeterminate quotient of the type 0 over 0 because f approaches 0 as x goes to a, and 1 over g approaches 0 as x goes to a because g is getting larger and larger. Rewriting the product as we have in the second case, we have an indeterminate form of the type infinity over infinity because g is approaching infinity as x goes to a, and 1 over f is also approaching infinity as x goes to a because f is approaching 0, and so 1 over that quantity gets larger and larger as x goes to a. And once we've converted this indeterminate product into an indeterminate ratio of either of these two types, we can then apply L'Hopital's rule. The other kind of indeterminate form that we're going to look at is what's called an indeterminate difference. Here we consider the case where the limit as x goes to a of f is infinity and the limit of x goes to a of g is infinity, and we're looking at the limit of the difference of these two functions. And again, it's not clear what this limit is going to be because we have an indeterminate form of the type infinity minus infinity. And again, our strategy for computing this type of limit is to somehow try and convert this indeterminate difference into a quotient for which we can apply L'Hopital's rule. And we can do this in a variety of ways depending on what the functions f and g look like. We might try and put them over a common denominator, we might try and rationalize them, or maybe factor something out. As one example of this is example 4.3.11 of the textbook. We're asked to compute the limit as x goes to infinity of e to the x minus x. We can see that this is an indeterminate difference because e to the x goes to infinity as x gets large, and x also goes to infinity as x gets large. And so we have a limit of the form infinity minus infinity. So our strategy here is to try and convert this into a ratio by factoring something out. And one possibility is to factor out x. So we get the limit as x goes to infinity. Factoring out an x, we have x times e to the x over x minus 1. How is that going to help us? Well, we can see we have two factors now, x and e to the x minus x over 1. Now the limit as x goes to infinity of x, of course, is infinity, so that's something that gets larger and larger. What about this quantity in parentheses here? What's the limit as x goes to infinity of e to the x over x minus 1? Well, that might be a little less clear, but what we can do is we can consider this quantity here, e to the x over x, and first figure out what happens to that in the limit as x gets very large. So in the limit as x goes to infinity of e to the x over x, well, now that's an indeterminate quotient of the form infinity over infinity because e to the x goes to infinity and x goes to infinity. So we can apply L'Hopital's rule to that. We have the limit as x goes to infinity of the derivative of e to the x with respect to x over the derivative of x with respect to x, and that's the limit as x goes to infinity, while the derivative of e to the x with respect to x is just e to the x, and the derivative of x with respect to x is 1. So the limit as x goes to infinity of e to the x over x is equal to the limit as x goes to infinity of e to the x, and that's infinity. How does that help us? Well, we can go back to our original expression now, and we see that what we have is the limit as x goes to infinity of x e to the x over x minus 1. Now we know this first factor, x goes to infinity as x goes to infinity, and we now know that this second component, the part in parentheses here, also goes to infinity as x goes to infinity. That's the product of two things that are both getting larger and larger as x gets large, and so the limit of this quantity is infinity.